Hello and welcome to this video on why it is that carbon dating is slightly flawed but still a very powerful tool in identifying the date of objects, samples and more. Carbon dating is an important tool in archaeology among many other fields. The basic premise is that the carbon builds up in certain things. The isotope of carbon that builds up at a given time is relatively specific to that time. What makes an isotope just that is a difference in the number of neutrons in the nuclei of an atom. The general understanding of an atom is that they have an equal number of protons and electrons. This leads to a net neutral charge. That is, as stated, not the case. This is also why most, if not all, elements on the periodic table have a weight just slightly different from a full number. Carbon as the topic of this video being 12.0096 grams a mole, and not just a round 12. The degree of isotope creation varies by history. This is because the isotopes vary on the amount of cosmic radiation the source was exposed to. Since this was a development in the 1940s, we must also consider that the atomic testing that followed over the next 50 or so years might have altered the quantity of various carbon isotopes. This does, however, bring us to what carbon dating, as it's properly called, is. An animal, plant, or area will have carbon deposited. This is a result of consuming things in general, whether photosynthesis, the creation of just parts of your body, anything really. This will always be a mixture of carbon-12, or the typical carbon, let's say, and carbon-14, which is an isotope. Once the animal, plant, or event stops or dies, the carbon stops being deposited. The basic premise is that all organic, that matter some inorganic matter, has carbon present. By taking an isotope, typically carbon-14, and measuring the proportion, and in some cases comparing to the average carbon, you get a rough value. The less carbon-14, the older the sample. More specific tests over time led to the creation of a calibration curve. That is a line that corrects your value based on atmospheric carbon levels. It got even more specific though, which is fortunate because this is a rather important caveat to the whole process. When calculating this value, you must adjust for the half-life of carbon-14. That half-life is known to be 5,730 years. Therein lies the first problem. With such a relatively short half-life, you can only go so far back in time. In fact, it's generally accepted that the limit is about 50,000 years. After 50 millennia, 99.8%, if not more, of the carbon-14 is gone due to that half-life. This means anything older than 50 millennia and you are struggling to get any kind of meaningful measurement. A measurement of radiocarbon was originally done with beta counting devices, and these effectively counted the amount of beta radiation emitted by the decaying carbon-14. The method is both somewhat tedious and slow. The more recent approach has actually been rather more simple. You use accelerator mass spectroscopy, and this is pretty much the default option now. It's simply faster, easier, and doesn't require waiting on a particular sample to undergo its half-life. And not just that, but you can get away with a much smaller sample. In fact, individual seeds can be tested this way, and so you don't need to destroy anything, at least not anywhere near as much. This does bring us to another problem as well, and that is, contamination, quite simply. This is an argument often used by creationists when confronted with radiocarbon dating samples, or alternatively used to argue for a few thousand-year-old Earth. Let's use a simple example. Mollusks, otherwise known as a shellfish. They use carbon in their shell. When they die, they get cannibalized or eaten by fish. On rare occasions, they get fossilized. Before this, they use carbon in their shell. This means you can date the mollusks reasonably clearly. The problem is that because you have this communication or exchange of carbon after death, you get some of the carbon building up in different species in different ways. In other cases, because they use environmental carbon, you get old limestone or other environmental sources of carbon being eroded and broken down, depositing them into living beings long after that period. This leads to an at best mixed date, or at worst a misrepresentation of the date. The solution to this is actually rather simple. The first is to compare to other similarly located but more permanent things. It could be comparing artifacts in a tomb, animals that don't use environmental carbon like mollusks such as skeletal remains of fish, boring to get rock samples, or basically creating a massive pile or pipe with compacted dirt and other material in it that you can then measure the appropriate amount in to see if your sample lies somewhere along that line that just doesn't make sense compared to where you found it. Things like this make it less susceptible to contamination. And the other option is simply not to use carbon. Potassium-argon dating is an example, and more so when we go back to the more than 100,000 years problem. That's because, again, at 50,000 years, you now have a problem of getting a reliable reading. Uranium's even further back again. Uranium dating either goes terribly wrong, since they end on a date that is an explosion, or a relationship up to 34.5 million years ago. It's often the latter. The next and similar issues related to wood. Mine's out of the gutter. It's a different kind of wood. We're talking about the outermost rings of a tree. That's because that's the only part of a tree that is growing. That is, each tree ring on the outside is the only one that'll have carbon deposited into it. So unless you have the outermost ring of a tree, you don't actually get an accurate date. This wood simply demonstrated by the cleaned and dressed wood used for furniture. It just won't have wood from when it was felled and processed. This would artificially push back the date of that particular piece of furniture by a significant margin. Other examples are when wood is repurposed or recycled. It might be far older than the new use, but it's impossible to know because, well, you don't know when it got turned into whatever it is. The other issue is that trees and, well, similar things only grow at a given time. After this, they stop, and before this, they also don't grow. That leads to a limited period of growth in each year, where wood is actually absorbing and using carbon, leading to a significant period where you just don't have data. You also therefore can only reliably say that there was this much carbon in the atmosphere that got turned into, well, whatever it is, in the case of a tree, cellulose, or parts of a cell, or whatever it is, at that particular time of the year. This is also why the more specific carbon date given by a report, the more skeptical it should be taken. The more specific the date range, the harder it is to get. This is to say it is not impossible, just very hard. The last major problem is related to more modern samples, and that is carbon deposition variability. A simple example is modern CO2 emissions. They are hugely increased. That creates a flaw as you have a huge bump in the amount of carbon-14 being deposited in plants at the moment, or in rocks and strata and similar. It artificially inflates the amount of carbon-14 on anything that is exposed. Historically, it's not just limited to gas emitted by industry like with industrialization. You must also consider environmental factors, things like volcanoes, acts of destruction such as razing cities, and natural disasters like forest fires. These are just a few examples of how you could get carbon contamination. Now, again, by doing things like, say, matching samples or cores, where you know if there was a sudden increase in the amount of, say, ash being deposited over a large area, and you know that there was tectonic activity, you could say volcano. Or if you know from records that a city was destroyed because the Romans were pissy one day, well, you know that that's not the issue here, rather that the sudden increase in carbon-14 was simply because, well, someone's house got burnt down, and then a bunch of other people's houses got burnt down. And things like that. This is radiocarbon dating in a nutshell, the good, the bad, and the somewhat ugly. While somewhat flawed, it is still a very powerful tool in archaeology, climatology, ecology, geology, and more. A tool, while flawed, is not a failure, but in some cases it does need corroboration by other evidence, and particularly in some cases where there may be confounding events that have disrupted the reliability of the results. And this is true when you're after very narrow time ranges. When you're after rather more broad time ranges, it's actually incredibly efficient and reliable. Thank you for watching this video. If you found it interesting, consider liking, sharing, and subscribing. Please do post any comments, questions, or suggestions you have below.